Hello there. How's it going? I am going to talk about vehicular communication, vehicular networks, vehicular ad hoc network, VANETs simulation in ns3. And in this example, I have a very comprehensive code. I mean, it basically runs basic tests that are very useful for you to get started. I am sharing this code on my GitHub, public GitHub, and you could basically clone the repository and do whatever you want with the files, and that will be supplied in the video description down there. So vehicular communication relies on what's called WaveNetDevice. Wave is wireless access in vehicular environment. Wave, right? We say wave, or DSRC, dedicated short radio communication. This is a simple example, and I'm going to create 3 nodes, 3 stationary nodes. I'm not sure why I'm supplying the command argument. It's not needed for this example. And from the get-go, I create the 3 nodes like usual, and then I'm going to use the mobility helper to set their position. Remember, wireless communication requires a position, even if it's constant position. They're not moving. Those nodes are not moving, but they have a position so that signal can be calculated properly. And then we set that mobility according to this allocator. So we put them at these locations, and I believe the unit is meters. The way I do vehicular communication is by using Wave Helper and WaveNetDevice. Some people use Wi-Fi Net Device, and I believe the most recent versions of Wave are WaveNetDevice. It's now a subclass of Wi-Fi Net Device. I'm not sure, but maybe 3.30 has changed. So basically, this is similar to what we did with Wi-Fi. We use the same YANS Wi-Fi channel helper. I'm calling it Wave Channel, and with default parameters. So for the propagation delay and the propagation loss follows these models. We could set it like that, with set attribute, but just leave it as a default, just for simplification. There is YANS Wave Phi helper. So this adds a little bit to it. And basically, we are creating an error model, and we're creating one physical, I think it creates one physical entity, 2 into a single channel, the CCH channel, which is the control channel. I'm not talking about multi-channel operation here. And set the PCAP format to radio tab. Basically gives me more information in the PCAP file, makes it very nice. We can set the transmission power between 2 ends. So this is the maximum transmission power we can use. And let me just set the minimum to 8, for example. And what happened here is that Wave allows you to have per packet transmission power. And that's very useful. Like sometimes you detect congestion in the network, you might want to reduce your transmission power. So I believe this divides the transmission into 6 or 7 levels, where I think 1 or 0 is the lowest and 8 or 7 is the highest. Okay. For the MAC layer, we use QoS Wave MAC Helper. And this basically creates the OCP Wi-Fi MAC, which is the MAC implementation for wireless access and vehicular environment Wave. Do I toggle source header? I believe there should be some OCP there, if I'm not mistaken. Yeah. So it sets it to OCP Wi-Fi MAC, object factory method, sets QoS supported to false in the case of an NQoS Wave Helper. So if you do QoS Wave Helper, then QoS supported is set to true. Going on, for communication, the Wi-Fi station manager, I'm using constant rate Wi-Fi manager. So this is not the AARF. And I'm setting the default Wi-Fi mode. So orthogonal frequency division multiplexing rate is 6 Mbps, and bandwidth, the width of the channel is 10 megahertz. Data mode, control mode, non-unicast mode. So this is for broadcast. I'm using the same, and this is for unicast. I am yet to determine which one does the control mode, or maybe I knew it and I forgot. This also uses the same. All these helper use object factory method of constructing objects. And then we install. So you could see the pattern here. We use a helper. We for CSMA-NET devices, for Wi-Fi net devices, we set a helper, and then we install at the end. And for the Wi-Fi and Wave, the vehicular communication DSRC, we needed to have a little bit more when we talk about MAC and physical layer. All right, I'm going to enable PCAP for called WaveTest devices. Okay, and that's it. We set up vehicular communication. We set up DSRC. The nodes are stationary, so if you want to implement your own, if you have some motion, you will, probably need to have some certain scenarios, and maybe I'll do some video about mobility. There's constant speed and constant acceleration and so on. So we'll create an empty packet of size 100. I'm gonna get the broadcast address for MAC48. That's all Fs. Okay. I'm gonna set the Ether protocol to 88DC, which is WSMP. I'm gonna set the transmission info. So I could set transmission parameters. In this case, I'm gonna set the channel number to CCH. So I could set things on per packet basis. So I'm gonna set the channel to CCH. Notice that WaveNet devices are tuned to one channel by default, CCH, the control channel. For multi-channel operation, where you alternate between two channels, I'm not discussing that there, but you could do that with different multi-channel schemes defined by 1609.4. I'm gonna set the TX parameter data rate, so I could set per packet data rate. Basically, what happens here is that we're using different encoding. If we're using a lower data rate, packets usually have travel further, right? But if you use like the highest maximum, it's 27. There are certain OFDM Wi-Fi modes you should use. I think there are like 8 of them. So there is 3, 6, 9, 4.5. 12, 18, and 27 and 24, I think. We could also determine which one of the queues, outgoing queues, are we gonna in-queue this packet. So I chose here to queue it at the highest priority, which is VO, voice. As you can see, these are the levels. If you look at the standards, that's how they're created. Basically, this has the lowest priority, meaning that the wait time between each frame, every time the node sends a packet and it has a stream of packets to send, it should send a packet and stop for a short time. It's called interframe spacing. And voice has the lowest time between frames, and this has the highest. Additionally, nodes contend for channel access because they do the channel sense. And if the channel is busy, they back off for a random number of times, and then you count downwards to that. And there is that you can actually set that slot time. So let's say you generate a random number 4. So and the slot time is like 32 microseconds. So it counts 32 microsecond, 32 microsecond, 32 microsecond 4 times, and then attempts to access it. So each one of these queues have different ways of generating that random number and different amount of time to wait between the frames. Look at the standards to get the information. So in this case, we can also set the transmission power, and I'm setting it here to 7. I think this is the highest. As you can see, it will use 33 dPm, I think, or decibel, as opposed to 8, the lowest one. So what else? And that's it. I'm gonna send my packet, my frame, using the device object. So I'm gonna get the zeros device and dynamically cast it to WaveNetDevice, and then use this object to send packets using the sendX function of the WaveNetDevice. At the first second, I'm gonna send a packet. Destination is the broadcast. All the packets I'm sending here are broadcast. And I'm gonna schedule some other packets as well, starting from T0. So I'm gonna create a packet of size 400 and a packet of size 250. And I could set the power here to 7. I could set so just randomly, depending on the number. One time I'm gonna send with 27 Mbps, other time and with different priority, then send that packet, and then change the priority, reuse that object thingy, and send a lower priority packet, and so on. And also I'm gonna send X a packet just using the default values, basically the default parameters that were set initially here. So not really the default, but the ones I set. I can also send a unicast, but that's not interesting. Probably not a lot of research with this. I think it's not desired. When you send a packet, you have to wait for acknowledgement, and everyone else have to wait for that acknowledgement everyone else has to wait for you to receive that acknowledgement, which is interesting. But we could do that as well by specifying a target MAC address. So I'm getting the D2, this is device 2, another device, net device of these WaveNet devices, and I'm just gonna get the target MAC and then target it just like how we send it here. The simulator schedule takes the time, and then I'm using the WaveNetDevice sendX function. You could look at this function. It takes as a parameter the packet, destination address, the protocol, that's the Ether protocol, and that TX info struct, which has the transmission parameters. We got to something interesting. I showed in the Wi-Fi example monitor sniffer RX. As you can see, it is part of Wi-Fi Phi. Now in WaveNetDevice, in Wi-Fi net device, it was Phi only, right? Because there's only one physical entity. In WaveNetDevice, it is defined as a vector of values, Phi entities, physical entities. And then we have to have a star here to match them. But the way ns3 is implemented, really, there is only one physical entity. I think they were foreseeing a time when they implement multiple physical entities, because there are some devices, actual DSRC radio devices, that has multiple. And the callback is the same. Notice that this has changed in NS 3.29 or between 3.29 and 3.30. So if you're using older NS3 version, this might not work. You might need to play with it a little bit. I'm gonna also call a trace physical RX drop. So this is in Wi-Fi Phi as well. For Mac, there is also a bunch of Mac entities. So with Wi-Fi net device, it was only Mac. For WaveNet device, Mac entities, it's a what we call a what's the word? It's a vector, and this will match 7 values. 7 for each channel of the Wi-Fi. There is a Mac entity created of type OCP Wi-Fi Mac. So I'm also want to match OCP Wi-Fi Mac, and here I want to match WaveNet device. Every time a packet is enqueued, I'm just gonna trace it here in a function. A packet was enqueued and dequeued as well. So this is basically tracing things on the Mac. Interestingly here, let's look at the signature here. The signature for this MAC entity, sorry, the callback takes Wi-Fi MAC queue item, which is good because I can get information about the queue itself, its size and whatnot. And basically DQ trace, a packet might get dequeued if it was, to be dropped, or there is also a drop trace as well on the MAC layer. Actually, I can, with this Wi-Fi MAC queue item, there is item.get, I think there is get packet, sorry, or get destination address. I'm not getting the queue, sorry. Did I say you're getting the queue? You're getting the queue item. You can actually get to the queue if you want from the context, and I will basically you could use the name and do it. I have an example where I do it, but it's a little too complicated to discuss. Okay, and so if we run this, I will share this with you, and this is the monitor sniffer RX. I just called it RX. So this is the channel frequency, the mode, the signal and noise, and just print the destination and source. All right. The way this is run, I actually have a very neat way. I have an alias R, which runs my latest modified project. And if you look at my repository, GitHub repository, I actually share that Python code that runs this. So the latest, so this basically runs this command for me. All right, as you can see, we have a packet was queued, a packet was queued, a packet was queued, enqueued, and then the enqueued, sorry. It says cannot have TX power not equal TX with TX level. Oh yeah. So I need to set the TX power levels. Forget about that. Where is my TX power start, TX power wave fee that set. I have to see how this works because it's a physical, it's a phi function, and it's called set n power. Let me look at the documentation. This is what you should do. Set n power. N power, something like that. N level. I'm gonna go to Wi-Fi fee to look at it. So where is it? Levels. Get NTX power. So NTX power. Set NTX power. So set NTX power. So I have to specify how many power levels do I have. So I am gonna see if this is actually, if I want to see if this has a trace source connected to it so that I can just conveniently, oh yeah, TX power levels. Okay, and what do we do? The type here is unsigned integer. Okay, and you can see it's set to 1 power level. And so what do? We go to WaveTest, and I'm just gonna go like this. Set for all the physical entities. What was it called? NTX power. So for every matching TX, do this, and I'm gonna say keep integer value. Let me say 7. Okay. I think this will set the number of because you have to have a you define the lowest and the highest. I messed this up somewhere. Where was it? 145 around there. I added some code that I didn't do anything with it here. So between 33 and 8, it will divide it to 7 levels, for example. So that's how it's done. So it will determine the step mathematically. Okay. So as you can see here, when a drop happened, it says packet RX dropped. So I do have a drop, right? I'm tracing drop, RX drop. So I have a packet and I have reason. So actually reason here is one of those reason unknown, whatever. They're determined in Wi-Fi fee class. But also this was only implemented in ns3.30, so it will not work with older ns3 versions. Okay, I can have more information. So reason here was some reason 2, whatever that is, probably collision. Okay, and basically I'm tracing things, so I have a lot of control over the simulation environment. You know, I'm computing a queuing delay, so every time a packet is enqueued, a timestamp is attached, and where's my DQ? We are consulting that timestamp. So item with the Wi-Fi MAC queue item, we can get that timestamp and compare it with now, and just print out the queuing delay. All right, I think that's enough. I'm 22 minutes in. For an example, basic example, I will share this on my what am I call it? GitHub repository. The number of power levels to share with everyone. Let me open WaveTest 0. Let me just show something. So as we can see the packet received, I could actually see the signal here, 3097, right? 3097. So that's received. That's the first packet, 3097. So if I tone it down, I should expect a different value. So I never set that. Let me set this to 3, for example. Okay, tone it down and run the last modified program. And let's open this. We say 3097, is it? Oh, it's the same thing. Yeah. Probably I have to get the right one. But yeah, I'll be sharing this code online. You can play with it as you wish. Oh yeah, it's set here to 7. Let me set it to 3. Okay, let's run this again. I hope it's different. Yeah, so it's different now. It's not 30, it's minus 47, 97. The noise is the same, but the signal is a little bit weaker. Okay, the channel and everything. And as you can see, there are different rates. So here's 9, 6, 27, 12. So I have a per packet parameters. Okay, I could go on forever, but you need to monkey around with it, play with it, and learn a few things and ask a few questions to get where you need to go. Thank you very much, and I hope you enjoyed this. Like this video if you liked it, and have a good day.